is here. Well, happy to have him here giving the seminar. So for those of you who don't know him, he just started here about a month ago as a postdoc. He recently completed his PhD under the supervision of Brian Patel at the University of Pittsburgh. He's been here for about a month, as I said. We're going to learn about N-naturalness from him today. I know I'm going to learn something new. I'm really excited. So give me your attention. Take it away, Mudit.
Thank you. Today I will talk about like this model and naturalness, and I will talk about like the gravitational wave probes of this model. So this was a work which it's the work which I'm like currently doing with my PhD advisor Brian and our two postdocs at PIT. So I can just start.
Just click on the screen. Then
I think it's like saying something like the meeting is recorded.
You can put the down arrow, I think. Right arrow.
No, okay.
Or scroll down.
Okay. Yeah, so first, just to give a brief motivation of like why we are trying to think about this model. So there is this idea called like naturalness, in which like in a very general sense, we say that whenever there is an EFT, then we want the EFT should not be very sensitive to the structure of the underlying UV theory. And basically there should not be like a lot of fine tuning in the parameters of the EFT. So as an example, what we will try to motivate ourselves from is like the Higgs mass square value. So if you look at the Higgs mass and we just in the standard model, there's like this one loop, let's say of the top or any other fermion, and it scales as like it is quadratically divergent. So if there is some cutoff in the standard model, let's say some lambda UV, then this mh square will be proportional to lambda UV square. And basically there has been like no evidence from like our LHC and other experimental probes of any new physics at the TeV scale. So if we assume that there is some new physics lying nearby, let's say at 10 TeV, so then we will have to explain this that why the ms square is not like of the order of around 100 GeV instead of like scaling as like lambda UV square, which may be 10 T square. So this idea of like this is called as a small hierarchy problem. We are like not really trying to answer like the large hierarchy problem, which affects like suppose the effects coming from the M blank. Basically, like if the quantum gravity comes into the picture. So if we are trying to deal with the small hierarchy, then we can so just to deal with the small hierarchy problem, there was an idea proposed by Arkani Hamad and his collaborators in 2016. And basically, in this idea, we have, let's say, n number of copies of the standard model, in which n is large and can be like 10 to the 4 to 10 to the 16-ish. And in all the copies, we have the same standard model structure, with like the only difference is in the Higgs mass parameter. So in this idea, like the lightest of the sector will have the weak scale, which is parametrically smaller than the cutoff of the theory, and this will come out naturally. And our standard model will be identified with the smallest, like with the negative squared mass value. And what we do is like we try to explore like how we can probe this model using the gravitational wave signatures. As an example, suppose if your n is 10 to the 4, so then like the quantum gravity effects are important at around 10 to the 16 GeV, and we set our cutoff to be like around 10 TeV. So and we are only worried about this cutoff, and we assume that there is some other completions which will take care, let's say SUSY or anything else above that scale. So and finally, like for all the n copies, we also have one more ingredient, which is like a Reheaton field. So basically, the idea of having the Reheaton field is to dump most of the energy after inflation to our standard model, because we want our universe to be populated, like the copy to be our standard model rather than any other copy. So we will see how that happens.
So is it just a simple coincidence that so we are sitting in our current standard model, supporting its naturalness? So in the third the idea we were saying our SM is to identify
Yeah.
sector with the smallest negative square height Higgs mass, then is it a negative? So according to the naturalness, is it a coincidence?
I don't think it's a coincidence. It's just like you have, let's say your mass mh square goes from minus lambda to plus lambda, and you assume some distribution. So then will identify it because like the SAM model will need to have like the most energy dumped into it to populate it and like to have life in that copy. So we will see why that is picked.
Okay.
So just to like give the model more concretely, so we have let's say m copies, and the mh square the mass square parameter ranges from minus lambda square to plus lambda square, and for our distribution we assume it to be kind of linear. So you can see this equation, this one. So this is our distribution. So for I equal to 0, this is our Higgs. So if you put I equal to 0, you have like minus lambda square r over n, that is our standard model value. So I equal to 0 is our sector. And then in addition to these copies, there is a scalar reheat term. So you can also have like fermionic reheat term, but we only focus for scalar reheat terms in our study. So basically this will dominate the energy density after the inflation, and it couples democratically to all the copies with a small coupling A. So it's like A phi h square, and then there is a mass term m phi square. So just to show pictorially what I mean, so basically we have like these n sectors, all of them have SU3 versus SU2 versus U1. The I equal to 0 is our sector. So if you go on this direction, like I greater than 0, and I goes from minus n by 2 to n by 2. So then in all the other copies, the mh square is heavier, and the wave is also heavier than our wave. So the wave square scales as proportional to I. If you go on the other side, then the mh square is positive. So there's actually no symmetry breaking happening using the usual maximum high potential, and your wave is actually very small, and it becomes like the wave becomes non-zero once your QCD becomes strong in that sector, and basically the VI, like the wave of that I sector, is proportional, and it's approximately like much more than the lambda QCD of that sector, and which is like of the order of 100 MeV. So wave is even lighter than 100 MeV.
I'm sorry, what does it mean u close to 0? What does it mean?
Oh, I just like wanted to say that this is like much smaller than suppose let's say order GB, like order 100 GB.
And you have negative mass.
So like here we have like let's say minus mu square h square plus lambda h raised to 4, and here we have like plus mu square h square plus lambda h raised to 4.
So it is not astonishing for you, just minus square of mass should be positive. Why it is negative?
I mean, I don't also have a good reason why it should be negative, but it is like how.
Minus 88 gives.
Yeah. So this
I
is.
cannot understand why it is why is it negative?
Oh, I think like I just mean that. So I think like it's the way I've written it, but so this is like when you write down the mu square in the Lagrangian, it is 88 square. Like the mu square is positive, it's just like the sign outside. So you can like put the sign here. So it's like minus mu square h square plus lambda h raised to 4, and the mu square is 88 square. Yeah, so like some of the key features of the model is that the reheat down decays preferentially to the lightest wave. So basically the ratio of the rho is the energy density of the decay into the ith sector, and what we find is that the rho I over the rho sm is the energy density dumped into our SAM model. This is like proportional to the ratio of the branching ratios to the ith sector versus the sm, and this is less than 1, and this we will see why. And also like the coupling A, it is small, it scales as like lambda h over n, and this ratio is independent of this coupling A. So the coupling strength is only important in controlling the reheating temperature, and all we need this for this scenario to work is that the reheat temperature is less than the Higgs wave, so we take it to be around 100 G. So basically our naturalness cosmology will be completely determined by two parameters. One is like the m phi, mass of the field phi, and the parameter r, which goes like in the scaling on the different sectors, and R goes from 0 to 2. And what we see is that because the coupling A is small, therefore the coupling to the other sectors are small, very like weak, and it makes the collider searches to be very like almost not there. So that's why having a gravitational probe is important for these kind of models. So just to give a brief summary of like the decays of the reheaton. So when I say standard model like sectors, it means like all the sectors in which I is positive and all the sectors have the usual symmetry breaking structure. The only difference is like the wave is like heavier and the mass of the Higgs is heavier in that sector. So in these sectors, the phi mixes with Higgs H, and let's say the angle is theta. So the phi decays to all the standard model particles in a similar fashion as Higgs, just with like a attenuation of the theta square. So you can see like this is the decay width when Fi in the scale says like theta square times gamma, and this is proportional to 1 over mhi square, where mhi square is the mass of that parameter in that I sector, and basically it scales as 1 over I. So for the standard model, this will be like the largest, and as we like go on higher and higher, it becomes lesser and lesser. So therefore, like the dominant decay is towards standard model. The energy density, if you add all the sectors, like the energy density dumped into them, so that will be like summation of over 1 over I, which is approximately like a log of n. So it is like small. Now we can also talk about like the decay of the reheaton field phi to the exotic sectors. So here the first thing is like there is like no mixing going on between the Higgs and the phi directly. So like in the mass against state basis. So what we do is like we will have to work our system in the doublet, like in the unbroken phase. So most of the decays they go via one loop, let's say like of H, and then we have W's coming out. So it can decay to W's and B. And the key point is that the gamma I, like the decay width, it scales as 1 over mhi raised to 4. So it goes as 1 over I square. So it's even getting worse as you go to like more negative I. So in this, for the exotic sectors, the only sector which is relevant is like the lightest I equal to -1 sector. And so this is like the sector which is important to us, and we will be like focusing on this sector because the rest of them are like have very less energy density to cause any substantial signals or effects. Yeah. And to move for most of the parameters, pardon?
Mass of this.
So this reheaton, like we consider between let's say around GeV to like 300 GeV, but like so it's mostly like near the ballpark of the Higgs. Yeah.
You just said that mass for everything, like that mass is set.
It's like an input parameter.
It's just a,
Yeah. So there was only like two input parameters like M, phi, and R, and I will talk about like some other input parameters later. But right now, like M, phi, and R are the input parameters. So just to give a summary of how this decays work, the blue is like for our standard model like sectors, and basically they scale as like, so this is my ratio rho I over rho S standard model, and it's like 1 over 4. So this was like 1 over I, so it becomes -1 over 4. And like when I becomes extremely large, then it goes as -1 over R. The bumps you see are just because like the quarks in those sectors are becoming heavier than M phi. So basically like that decay stops. So that's why you see some bumps. So at first is like bottom, then charm, and then so on. And this is like a plot for like when I fix M phi to be 100 GeV. The purple line is for like the exotic sectors. So here the scaling is like, as I said, like 1 over I square. So if I have 1 over 4, then it's like -1 by 2. And as so therefore like the first sector is kind of important, and then you can see even like for like the next sectors, it's becoming even less than like 10%. So that's why you can like, kind of ignore them. So now we can like just briefly describe the cosmology. So the cosmology of the standard model sector, so they are similar to like the cosmological evolution of our standard model. The only difference is like in the masses. And also important point is like that we assume that there is no baryogenesis happening in the other standard model sectors. We like don't really have a model right now to like prevent it, but so like this is like an assumption right now. as I said, like the heat temperature of the SAM model is fixed at 100 GV, and we are taking n to be 10⁴ in our study.
What is mean temperature here? What is, how do you define it?
So like each of the copy will be in a thermal bath. So like if you, so what you can do is like you can define the temperature in the SAM model, and then you can use some, let's say chi I parameter for all the I sectors. And then using your temperature as like the one coordinate, you can try to do some calculations and like.
So it's statistical. So it is normal statistical.
Yeah, this is like the thermal bath temperature of the SAM model. And we just want it to be like below the Higgs wave. In the sense that we don't want any thermal contributions in this story. So now just to give like a brief idea of how the first exotic sector looks like. So this is like the mass spectrum. So basically what is happening is like you start from the T reheating, and then as the universe expands, there's some cooling down happening. And when the temperature of the -1 sector, it hits the critical value of 85 MeV, around 85 MeV, with some, I think, 20% error. So then when this happens, there is formation of quark condensates, and the quark condensation actually leads to a spontaneous breaking of the SU2 symmetry, because like whenever there's quark condensation happening, it will lead to a generation of a tadpole term for the Higgs, and that will lead to a symmetry breaking happening. And that's why like the the wave in this sector is scales as f pi cube over mh square, and this is much less than our usual like the wave that we have in our mind. So when this happens, there's also like breaking of this approximate chiral symmetry of SU6 cross SU6 to a SU6 vector, and in this case, like the 3 of the goldstones are eaten by W and Z. So the W and Z actually get masses from the goldstones of this global chiral symmetry, and that's why like the MW and Z, they will scale as around like of the order of f pi, which is of the order of 10 MeV. The rest of the pions get their mass from the explicit symmetry breaking through the Yukawa terms, and just as a scaling, those pions will range from, let's say, a keV to a MeV. Then finally, the leptons, they are like the lightest, and they are just like the Yukawa times this wave. So the mass of electron is around 10⁻⁴ electron volt, muon is 10⁻² electron volt, and tau is 10⁻⁻1 electron volt. So as you see, like all the particles here are much lighter than their SAM model counterparts, and they will have some different kind of cosmological evolution and effects. So pictorially, this is like what I meant. We start with like the phi decaying to our exotic sector at T reheat. The new Earth expands, hit critical, then W and Z decouple from the thermal bath around keV of the 4. Then the neutrinos decouple, and finally, near the recombination, the tau and muons decouple. So near the recombination, which is defined as around temperature of around 0.3 electron volt, the exotic sector species, they consist of the photons, neutrinos, and electrons as well. So this is different from our SAM model, because SAM model like electrons are already out of the picture. And we take the critical temperature to be 85 MeV. We define percolation temperature, which is basically like when 1/3 of the universe is in true vacuum. So we take it to be less than 85, but in between like 50 MeV to 85 MeV. So now the important thing, and like which one of the important probes which constrain like the naturalness parameter space is delta n effective. So like phenomenologically, as we saw that because like the couplings are small, like the Coulomb searches are kind of not very helpful. So one of the important probe for unnaturalness is like the delta n effective during recombination. And for our scenarios and our benchmarks, like in the subsequent plots which I will show, we take the experimental bound from CMB, which is like delta n effective, we take to be less than 0.7. I think this is coming from Planck plus the H0 tension. So this is like our criteria. I will also show delta n effective of like 0.03 from the CMB stage 4, and I think 0.3 from just from Planck, but those are like just to give a better picture. So what happens is like all the SAM model like sectors, they have a contribution to the delta n effective via like the free streaming neutrinos in each of their sectors, and basically it scales as like the brand proportional to the gamma E over the gamma SAM model. So here I have like some all the I greater than 0. For the exotic sector, as we saw, like all the other like I in negative -2 to -n/2, they are like not really important because their contributions are small. So that's why I only include the exotic sector, and this scales as also as like gamma -1 to ratio of gamma SN. So on the parameter space, like how delta N effective curtails our parameter space. So basically on the right, I'm showing like R versus M5. So these are like my two parameters, and like the shaded region is corresponds to delta N effective total of like less than 0.7. So basically, if you agree that the bounds are on delta N effective is 0.7, then this much of the parameter space, like the shaded region, will be excluded. The solid curves are like bounds on the total N effective, which means like sum of all the sectors. The dashed is only on the exotic, like I equal to -1 sector. And just for a context, I'm also showing like some tighter constraints, like say suppose if you assume that the CMB plus S4 is the most relevant bound on delta N effective, then if it's like around 0.03, then all the parameter space from this red line will be excluded. Interestingly, I also show like a funnel region. If you see this region, so this is just on the right hand side, just like a zoomed out version. So here I'm like why the reason that the bounds are kind of like weaker in this region is because that the M5, it is in the neighborhood of the Higgs mass. So what happens is like the mixing to the Higgs mass is enhanced because the theta scales as 1 over like the difference between M5 and MH. So because the theta becomes larger, that's why like the branching ratio to the Standard model is much greater for this parameter space. So that's why like the delta N effective from the other sectors is not really important. So you get like some extra parameter space region.
Why does your exotic sector contribute so less in the R parameter for M5 less than? I thought the exotic should be comparable, but it's the kind of factor of 4 difference for the left one.
So you're like you mean like this region?
Yeah, why exotic is kind of for larger values than that?
I think like here because like the phi goes to H-1, H- will open up. So that's why like this will be more comparable. But I think here like all the decays are happening mostly through loops. Because like it's like the phi goes to a H and it's like a triangle loop, and then you have W's and G's coming out, or like W's and B coming out.
But you get all those BB bars and all this stuff at the end. It has to be
I mean like so we added all the contributions. Yeah, but I'm like
just
not
trying to understand why.
Yeah, I think like, so if this is equal and you have like a two body on shell decay, I think this has to be smaller, right? At least like slightly smaller. Okay. Okay. So now we can like move on and try to understand like. So we will just try to like give a brief description of the parameters which are relevant for the phase transition. So the assertion is that in a QCD with like 3 or more massless quarks, there has been arguments by Pesarski and Ilchek that it will undergo a first order phase transition. So in our case for the exotic sector, because the quarks are all the 6 quarks are massless till late, so if due to like whenever the quark condensation happens and there is a phase transition, it will be like a first order. So assuming that this argument is correct, then we can think of like what happens, like what are the gravitational wave signals from this first order phase transition. And the important things for the phase transition are like first thing is the critical temperature. So it is defined where like the free energy is kind of same as like the in the broken and unbroken phase. So this is the point where the phase transition should start. The Tn is defined as nucleation temperature. So this is the temperature at which like the bubbles of the true vacuum starts to populate. The Tp is like the percolation temperature. So as I said earlier, it is like the temperature at which 1/3 of the universe more or less is covered with the bubbles of true vacuum.
Do you connect critical temperature with some phase transition?
Yeah, so we have like
Which kind of phase transition do you consider?
So I think it is like the first order phase transition, and like we take the TC to be of the order of the lambda QCD in the -1 sector, and it's around 100 MeV. Does that answer the question?
So just question, is it standard?
Yeah.
The critical temperature for which from Landau gives books about phase transitions.
Yeah.
But which?
So this is just a
Okay.
visualization to show. So this is happening when like the basically whenever the quarks start to condense, like the quark condensation starts to happen, the symmetry gets broken from SU2 cross U1 to the U1, and that happens at around 100 MeV where the QCD becomes strong. So this TC is more or less of the same order as
What is the
lambda
value
QCD.
for TC? What's order of the values of TC?
So this is around 85 MeV with or 20% error. Like we can't calculate it like from first principle, but we know that it has to be of the same order as the lambda QCD in the -1 sector, and that has to be around 100 MeV. So like all these three values are of the order of let's say 52, 85, or 100 MeV. The other two parameters that are important are like the strength of phase transition, which is given by alpha parameter. So basically, it's a ratio of the difference in the free energy by the energy density in the radiation path. So alpha -1 is just for the exotic sector, and alpha total is for the entire copies of the same model, add them up. And the second parameter which is important is called the rate of transition. So this is defined as like beta over h. And I will tell you like what the values that we choose.
And what is V? Is this pressure, some kind of pressure? Or what is V? How to understand V of phi?
Yeah,
It looks like
this is just the potential. Like this is also this photo will actually like not work for QCD. This is just for illustration purposes. Suppose if you have like a scalar potential, so then V of phi will be like let's
but
say
it looks like usual isothermal for pressure as function of some.
well, I think the
Density.
pressure is also minus V, but this V is potential. But I think you are right. Like when you like write down the pressure is equal to minus V, and this
So
V is a
pressure is
potential.
connected to.
Yeah. Okay, so now we try to understand like what can be like some kind of gravitational wave signals from this phase transition. So basically, whenever there is like a cosmological phase transition, it can lead to a production of the stochastic gravitational waves, and there are basically like three different ways that we can do that. So the first way is like there's a formation of the bubble walls, and due to the collision of the bubble walls, there will be some gravitational waves. The second kind is like the production through the sound waves, which is happening from the plasma surrounding the bubbles. So this is like the second kind of production. The third is like through some kind of turbulence in the plasma. And what we see is that for our case, the first and the second, like the bubble walls and the sound waves, are the only relevant gravitational waves. So like the important thing is like we define this differential density parameter, and I think it is defined as like the ratio of the derivative of rho over the log of the frequency, and rho critical is like the critical density at that time. We also use like semi-analytical parameterizations. So basically, we like the gravitational wave produced at emission can be summed up as like, so BW is the bubble wall, like the first time, SW is the sound wave, and basically you see there is some dependence on this beta over h parameter and also on this alpha parameter. And I will tell like what the different numbers are for this alpha. And finally, once you produce them at emission, then you have to redshift it today because like we want to do our calculations now, not at like emission. So then you redshift it using this vector. So basically, so like now what is happening is that we try to study two different scenarios, and the reason is like ideally we would have like to calculate the alpha parameter and beta parameter from like first principles, but since like the transition is like you go from a perturbative regime to a non-perturbative regime because inside the bubbles in a true vacuum the QCD is strong. I don't think there is like good studies in which calculating alpha is possible as also and like applicable to our case. So instead of like trying to do a full calculation, we take a phenomenological approach in which we choose different scenarios and like logical choices which are at least consistent, and then we just try to say that okay, let's say this is the like one way or the other, these will be like the possible values of alpha, and then what can be the gravitational wave signature of those scenarios. So the first scenario is like this called runaway regime. So runaway regime is basically when the bubble walls they overcome the friction due to the plasma and they continue to accelerate. becoming ultra realistic. So that's why your VW, which is the wall velocity, is 1, and like C is set to 1. And in these cases, the gravitational waves are produced through the bubble walls collision, and alpha has to be large. So like there is like sufficient pressure in the accelerating bubbles. So this we call as the scenario 1. So basically V has to be 1 and alpha minus 1 has to be around order 10. The cup, and since it's like a bubble wall thing, the kappa is equal to 1 and kappa of sound wave is 0. The second scenario is the other scenario in which, let's say, if the gravitational waves are produced through the sound waves instead of the bubble walls. So in this case, the transition energy will be like dumped into the plasma motion, and the gravitational waves are sourced by sound waves. And we also assume like a local thermal equilibrium, and in which case there has been studies that alpha minus 1 has to be small and it has to be bounded. So as a choice of parameter, like to represent this kind of scenarios, we choose alpha minus 1 to be 0.3, and in these cases VW is approximately 1 over root 3, and then again that the kappa of, like since it's like sound wave, we calculate its value, it's like 0.55, and the bubble walls has to be 0. Also for the rate of transition, again, like we can't like really do a first principle calculation of beta, so we choose like a range, a physically motivated range. So we have to start, we take the values from, let's say, all the way from small as like 3 to all the way as large as 10 of 4. The large end is like motivated from, there has been some studies of QCD effective studies in which people think of like this Nambu Jonah models as well as the linear sigma models, and they kind of predict that for like the beta over h comes towards approximately towards the higher end, so it's like around 10 of 4. So these are like the motivations why we choose these parameters. So once we have like chosen these parameters, now I will try to show how it looks on the gravitational wave parameter space. So on this plot, you can see like on the y-axis we have the omega gravitational wave parameter. On the x-axis we have the frequency in hertz. So basically, like the blue lines that you see, and also this is like the scenario for the runaway transitions. So basically the gravitational waves which are produced due to the bubble walls. So we have, I'll show 3 different scenarios. So the first one, which is like the one which is proved by most of the experiments, can be proved by the most of the experiments, is like the case when beta over h is small, it's like approximately 3. The other scenario is like of beta over h of 10, and if you go for even like larger betas, then we basically end up in a region which.
What's the alpha value you chose for the nanograph beta over?
Oh, so I think like for runaway we choose alpha to be 10,
Okay.
alpha minus 10. Yeah, it's like towards the larger end.
Blank.
Yeah.
So, but is there like a study for alpha 10? Kind of easy.
I think we did choose like larger values. I think there have been studies maybe like of alpha of the order of 1.
Yeah.
Yeah, but I'm like, I think this was like more like a, let's say, optimistic case. Yeah. So as you can see, like the solid lines, like solid black lines, are the experimental lines which are coming from like LISA. So on the like towards the higher frequency side, these are like the interferometry based and or proposed interferometry based space observatories. So LISA, then BBO, and then MURS. And towards the smaller side, like we have nanograph in this nanohertz region, and then there is the proposed SK. So this is how like the runaway transitions will look like. For the second case of like the non-runaway, which basically means that the gravitational waves produced from the sound waves. So in this case, we choose like our alpha is small of the order of 0.3. You can really take it smaller, but then the hertz will shift down. So we choose like beta or h of 10 and 1000, and again, like on the y-axis we have the omega, and then x-axis we have the frequency. So now I will try to translate these to our n-naturalness parameter space and just show how it looks.
So you're talking about phase transitions, runaway or non-runaway,
Yeah.
or phase transitions.
Yes.
Okay. So how to understand? You should have some strong change of qualities near phase transition, right? So it should be. So what is really your omega? Why do you measure this at h bar squared?
One second. Wait.
Yeah, not here. Next.
Yeah.
Way and you
Yeah.
here.
Yeah.
So it first, why do you measure this quantity in h bar squared?
Oh, this is
why
not.
why do you multiply by h squared? You have very small quantities. And what is omega GB? What do you?
This is like the strength of the gravitational wave, not the strength, but like the gravitational wave parameter, which you define as the ratio of the energy density of that sector, or like of this exotic sector with respect to like the energy density of the radiation path as a function of the
Some
frequency.
kind of response, or could just I can't understand this.
Like in what sense response?
Could you consider omega as some kind of response function, just I don't know, a function of frequency, and how to see here some changes, some
Just
big
explain,
changes.
just explain what that quantity is
Yeah.
in like one word, because I think you're very confused about it. That's just the energy density of gravitation
Yeah.
relative to the critical density of the universe.
Ah.
Yeah, so that's just like, that's the outcome.
Yeah. Yeah, I'm not sure about the response function part.
Yes, sure. Thank you.
Okay. Yeah. So now we are going to like map like our gravitational wave parameter space into our like the naturalness parameter space. So basically, again, we have like the R versus M5 plane. R goes from 0 to 2, and like M5, we choose it to be like in these parameters. So like so the idea is like each curve on the previous page corresponds to some delta n effective, because delta n effective can be related to the alpha total. So what we are showing is that like again like the shaded region is like for delta n effective of 0.7. So you will be like not allowed by just from constraints coming from delta n effective. But now we can also put the constraints coming from our gravitational wave observatories on our perimeter space. So the idea is that you, let's say suppose we choose beta over h to be 10, and this is like for the runaway case. So for the line of beta over h of 10, if you shift it by changing delta n effective, like it shifts downwards like quadratically as delta n effective increases. So just to make these lines, you just assume that any point above will be probed by the gravitational observatories. So for the beta over h of 10, we saw that the important ones were like the SK, BBO, and URS. So we can translate those on our parameter space of R versus M5. And again, the point is like even though most of the space has been probed by the constraints coming from delta n effective, there is this wedge of space which was like not really probed by delta n effective, but could be, at least in future, could be probed by the gravitational wave observatories. So like the magenta is the SK, then the green is the BBO, and if you think that the mu-RS will happen, then even like the funnel region will be probed by the mu-RS. So this is like for the scenario if it was, suppose the case was of runaway. So suppose if instead like the phase transition and the gravitational waves are produced through the sound waves, so then we choose like a benchmark scenario of beta over h of 100, and again you can see that in the region which was like not really probed by delta n effective, you can have mu-RS or BBO which can probe these regions. So now I can basically like try to conclude. So the whole point of the study is, so first of all, the n naturalness, it addresses the small hierarchy problem which is associated with the Higgs mass square parameter, and by including n copies of standard model with a range of Higgs mass square. And what we find is that the first exotic sector, it actually undergoes a QCD phase transition, and the gravitational waves are peaked in like from nanohertz all the way from nanohertz to, I think it should be like hertz. And another thing is that the naturalness by itself, it cannot explain the recent observation of stochastic gravitational wave background by the nanograph. And I think there was also a paper which claimed that if you have phase transitions in hidden sectors, in general, they on itself cannot explain the entire nanograph results. So like the unnaturalness is also in line with the cell claim. We also find that the lot of parameter space of the unnaturalness can also be proved by this future PTI experiments like SK, not SK but others as well. And also they can be probed by LISA, BBO, and URS. And the idea is like earlier it was thought that the only way to probe was just using delta effective, but our study shows that the gravitational waves can do a complementary probe to this unnaturalness parameter. And just for like future, so firstly, like you would definitely want to understand more about how to study gravitational waves and like phase transitions in the strongly coupled theories, like from first principles instead of like trying to do a phenomenological job, but if we can actually do some calculations. And also we only consider the scalar field, the Ringleton. So I think there has been ideas with fermions, so we will try to explore it in general. And also I think there has been some papers by let's say Yang Bai and Andrew Long about like this quark nuggets. So there can be like variance scenarios in the exotic sector, which can give you some naturalness, like natural dark matter candidates. So I think this can also be a area to study in the future. So I think this was like all that I have to say. Thank you.
Okay, so questions for Mudit? Yes, Kevin.
So you mentioned that collider searches are hard to do for this type of scenario. Are there any other like terrestrial ways you can search for maybe the repeat on via mixing with the Higgs or anything like that? Or is it really only cosmology gravitational wave signatures?
I think it will only be cosmology or gravitational signal unless your phi is of the similar order, because like you need like a really large mixing, right? So I think until and unless your phi happens to be in like around the Higgs mass, because that's the only region when the mixing can be large, right? And also the coupling is kind of small. So the upper bound is like lambda h over n, and n is like at least 10⁴. So the coupling is kind of small. So like any kind of mixing, it will be small to the usual. And I don't think that can be probed in the terrestrial experiments.
How small is it? The coupling?
So like if lambda h is like if you take lambda to be, so it's like a dimension-full coupling. So it will be like in terms of like say and some energy. So it's like 10⁻10 TeV over 10⁴. So that's like the size. That's like the upper bound, and that's for like our n. But generally, like you can also go for like a bit larger n. So then your lambda h and n can like scale slightly. But I think that will be like the upper bound. So you can even have like even smaller A's.
So the lambda appears in the denominator.
No, lambda over.
Lambda over.
Yeah, I think it's like.
And then it's 10⁴.
Yeah, I think this is like.
10⁴, and then it's G.
Yeah.
Then 1 G.
Yeah, like if this is the. Yeah, if this is the parameter space. Like if this is what we choose.
So is it considered small coupling? I don't know. It's not dimensionless and dimension full.
Yeah, so I think you have to define some kind of dimension. And let's say like upper bound, so I think generally take it to be much smaller.
Much smaller.
Yeah, so like put some factor in front.
I mean, very naively, I mean, maybe LHC is not a way to go, but maybe, I don't know, maybe intersected frontier facility might allow the chance of getting some signal.
Yeah, I think like what I remember is like I don't think there is like much scope, but I can like take a look and then can get back.
Yeah. So yes.
Is it possible to consider fluctuations of mass in which you study near critical point? So the question is, you consider infinite system, and so you should get some kind of divergences, so, like in Landau theory, or just this analogy is maybe not so good. for fluctuations of mass of Higgs metal, just is it possible to study this for such a?
So fluctuations coming from exactly like what? Like what's the
Just to understand what we have near, what is the what is the peculiarity of critical point in your picture?
but I think I don't understand, like when you say like fluctuations, so in like
Fluctuation of mass, which you
yeah,
study.
but like from where, like what's the source of the fluctuation? Like, I just like want to see check.
For fluctuation of particle number or fluctuation of energies or just maybe it's possible to. I don't know. Just that it is.
Well, if the fluctuations are coming from the temperature, then they will be much smaller, right? Because like the temperature at which the transition happens compared to the Higgs mass, that scale is kind of small because the transition is happening at around 100 MeV, and the M is still at 100 GeV. So I think the naive temperature fluctuations will be small, and I'm not sure if like because that's the scale in the problem, right? So unless you have some other ways of getting fluctuations.
Yeah, but the question is, do you have divergences near critical point? Do you expect divergences near critical point, or you have some arguments for smooth behaviors of critical point? What I have no feeling of your critical point. What is really what is the peculiarity of critical point?
I think it's just like, so if I understand correctly, like basically like we are saying that the alpha parameter will approach 1 or like let's say 4 pi whenever like the lambda QCD, like the temperature become of the order of the -1, which is like 100 MeV. So like inside you have like alpha to be strong, and like in the false vacuum you had like free quarks hanging around, and inside you have like just mesons, so like pi whatever. So this is like the idea that we had, and now like I'm not sure, like if you ask like fluctuations, I'm not really sure like what's the procedure, like what's the process that you have in mind.
Okay, thank you.
Mudit, has anyone studied primordial black hole quantum? For this potential, so that could be another signal for this. Because yeah, I never studied this alpha beta this QCD potential.
I see. I don't think like I've seen like the primordial black holes from this, but I will like double check. But I will get back to you on that. I haven't seen that. Yeah, but I will like just do a deep search if there is.
Yeah, because there could be some other signals. Because people have constructed primordial black hole based on first order.
Okay.
And so those will, but for your alpha beta over science.
Oh, so you are saying like in different scenarios you can have different sizes.
Right.
I see.
And so the nanograph signal is corresponding to what size of it. And that could be your dark matter.
Okay. I think I will like double check.
So other questions? Zoom audience? Okay, so let's thank the Mudit again.